And we're going to go to here. How did it go with the video and learning how to write the double replacement reactions, reviewing that from last year? How did it go? It went okay? How did it go with writing the complete ionic and net ionic equations? You get it? You get it? Okay, cool. I'm just going to go through a couple things really quickly so that you can just see the pictures with them as well. Okay, so we're going to go to pages. We're going to start out on page 18. Okay, and this is of unit 0. Unit 0, page 18. So the first thing that we need to look at when we have a double replacement reaction, and this is page 18 in unit 0, is that we have a compound. What type of compound is it? It is an ionic compound because we have a metal and a nonmetal. So anytime you have a double replacement reaction, you're going to have an ionic compound. And what's that? AgNO3. It is a ionic compound because it's got a metal and a polyatomic ion. So it is an ionic compound. So you will always have two ionic compounds, and ionic compounds are always made of, guess what? Ions. Yes? So you can see the ions here and you can see the ions here. And when we're doing a double replacement reaction, our reactants are always going to be aqueous because it just makes our lives easier. Okay? And when they are aqueous, an aqueous ionic compound, what do aqueous ionic compounds do? Aqueous ionic always dissociate. Okay? Aqueous ionic always dissociate. Compounds just CMPDS. This is page 18 if you just came in the unit 0. So if we look at the NaCl, it's not going to stay together when we write our complete ionic equation. We're going to have to separate the ions. So instead of having Na and Cl written together, we're going to have Na and Cl written separately. What am I missing? I'm missing charges because they are ions. They're part of an ionic compound. So this is positive, this is negative, this is aqueous, and this is aqueous. So I also forgot my states. Anything else I forgot? Maybe a plus sign in between them. Okay? So there we go. That's our NaCl. How about the AgNO3? What should I do with the AgNO3? It is ionic and it is aqueous. What should I do with it? Dissociate it. So we're going to have Ag and we're going to have NO3. What am I missing? Charges. I got a plus and a minus. What else am I missing? States, aqueous and aqueous. And am I missing anything else? How about that plus in between them? Yes. Okay. Now, Draw my arrow in between. Remember, we are never going to use an equal sign in chemistry. We're always going to use an arrow. All right. Products. I have NaNO3. What kind of a thing is that? NaNO3 is aqueous, and it is also an ionic compound. So if we have an aqueous ionic compound, what does it do? Dissociates. And you can see the Na and the NO3 are floating around separately from one another. Yeah? So we are going to write them separately from one another. So we have Na plus aqueous and NO3 minus aqueous. I'm going to get rid of this because it's just in my way. And then our last bit here, we have AgCl. What kind of a thing is that? It's solid, but it's also an ionic compound. Do solid ionic compounds dissociate? No. So we are going to write it together. Okay? AgCl, solid. Now, what I would like you to do is I would like you to tell your partner if there are any spectator ions in this complete ionic equation. How do you know if there are spectator ions? Spectator ions should be identical on both sides. Are there any things that are identical on both sides here? Yeah, we got our sodium. And we also have nitrate. Okay, so we have sodium and we have nitrate. So our spectator ions are Na plus and NO3 minus. Those are our spectator ions. Now, in order to write a net ionic equation, what do we do with our spectator ions? We cancel them out. Okay, so in a net ionic equation, we cancel out the spectator ions. We basically just rewrite it without them. So what I have left is Cl minus plus Ag plus, right? And then over here, I have AgCl. So I'm going to write it like this. Cl minus aqueous plus Ag plus aqueous goes to AgCl solid. Now, I'll be honest with you, that bothers me a little bit, although it is 100% correct. Okay, you would get full credit for this. I personally like to write it like this, just because I like my cation to come first. It just looks nicer, but there is no actual reason that you need to do it that way. Does that make sense? Okay, so you can choose. If you don't want to bother switching them around, you don't have to, but you can if you want to. All right? So that is our net ionic equation. Now, there are a couple of special circumstances when we are doing double replacement reactions. Let's take a look at those two special circumstances. So on our next page, we have copper sulfate, which is aqueous. So the ions are dissociated. We have strontium hydroxide, so the ions are dissociated. And what do you notice about the number of hydroxides compared to strontiums? There are 2 hydroxides for every 1 SR2 plus. Now, when we go to make our products, do you remember what we do to find our products? We take our outside ions, so the one at the front and the one at the end, the one at the front and the one at the back, and we combine them. So we're going to take Cu2 plus and combine it with OH minus, and that's going to give us CuOH2. Okay, so we combine our outside ions, and then we combine our inside ions. So here's my inside ions, the SR and the SO4. And when I do the inside ions, I like to go backwards. And the reason for that is that's going to put my cation first, which is the order that it goes in. Yes? So I have strontium, SR2 plus, and I have SO4, which is 2 minus, which means that my compound that is formed is SrSO4. Is good? Okay. Now, if I go look these up on my data table, it turns out that copper hydroxide is low solubility, so it is a solid. But strontium sulfate is also low solubility, so it is also a solid. So this is a case where I have 2 precipitates. And yes, that can happen. It's not a problem, okay? So let's now write our complete ionic equation for this reaction where we have 2 precipitates. I have an ionic, aqueous. So when I have ionic and aqueous, what do I do with the ions? Separate them. So I have 1 copper and 1 SO4. So we have Cu2 plus SO4, 2 minus. And I should do something else there. Aqueous and aqueous. So that's this beaker right here, copper sulfate. In our second beaker, we have strontium hydroxide. And before you write this down, I'm going to write down something and you're going to tell me if you like it or not. Okay, number 1, we need some charges. What are we not liking? Yeah? Yeah. Are my hydroxides attached to each other? No, they're not. So you would not put the 2 down at the bottom. You would put the 2 in front, which shows that you have 2 separate hydroxides. Okay, and of course we still need our aqueous and our aqueous. And then we get to our products. We have a solid ionic compound. Do we separate the ions? No. So we will just write it as Cu. Oh, actually, what if I was to write it like this? What if I wrote CuOH2? How do you guys feel about that? You need to have brackets because if you don't, it means there's 2 H's, but it means there's only 1 O. The 2 doesn't apply, so you do need to have those brackets there. Okay? And that is solid. Our other product, again, it is an ionic solid. So we write it together. So SrSO4, solid. Now I would like you to look for spectator ions. My watch telling me I'm supposed to stretch and be more active. Too bad, it will have to wait. Do we have any spectator ions? No. When you have two precipitates, there are no spectator ions. Okay, so when we have two precipitates, there are no spectators. Okay? And if there's no spectators, then what is our net ionic equation going to look like? It's going to be the same as the complete ionic equation because there are no spectators. Okay, so if you have two precipitates, complete ionic and net ionic are identical. Next case. What if we have no precipitate? So here we have, if you remember alkali metals, whoever they pair with, they're always soluble, so it's aqueous. And oh, look, I've got nitrate, and nitrate is soluble with everything. It's always aqueous. So if I take my sodium and then pair it up with the sulfide, if I combine my outside ions, Na is positive, S is 2 negative, so we end up with Na2S, but because sodium is soluble with everything, this guy over here is still aqueous. Then I can combine my inside ions, my potassium and my nitrate. K is positive, NO3 is negative, so I just get KNO3. KNO3. But again, I have a nitrate, and nitrate is soluble with everything, and I have an alkali ion, and alkali is soluble with everything, so I have another aqueous substance. And if we look at the pictures, look, my ions, ionic, aqueous, it's dissociated. Ionic, aqueous, it's dissociated. And everybody is still ionic and aqueous, so they are still all dissociated. Have we formed anything new? Did I actually make any Na2S? Are my two NAs actually attached to my S? No, they're not. So even though I can write this to sort of like look and see what would happen, is this what's actually happening? No. So if both products are aqueous, there is actually no reaction. Yeah? So what would we write for the complete ionic equation? Nothing. What would we write for our net ionic equation? Nothing. And in fact, for our formula equation, we would also write nothing. All you have to do is write no reaction. So the answer to all three of them, the formula equation, the complete ionic equation, and the net ionic equation, they are all just NR, which stands for no reaction. Yes? So those are your two special cases. Yes? You can just write same as above. Yeah. You don't have to write it all out again. Yeah. So are we feeling pretty good about the double replacements? Okay. We're now going to take a quick look at single replacement. Now, single replacement is different because all my double replacements, I have an ionic compound plus an ionic compound. Single replacement, we're going to move to page. Why have I written on here? I wrote on the wrong one. Okay, that's all right. There we go. Okay. Sorry. Okay, here we go. This is on page 23. Okay, page 23. And when we have a single replacement reaction, we are always going to have an element, and then it is going to be plus an ionic compound. Okay? What do you remember about elements that are on their own, not part of a compound? They are neutral. So they have a charge of 0. So this is going to be different than the double replacements. In the double replacements, everybody always had a charge. Even when we wrote the ionic compound together, even though we didn't show the charges, like NaCl, you're not going to write the charges, but it was really Na plus and Cl minus, right? But here, when we have an element, its charge is 0. Now, within the ionic compound, we're going to have the metal, which is going to be positive, and the non-metal, which is going to be negative. Okay? So let's take a look at examples here. All right. We're going to start with some zinc. We are going to assume that this is all taking place in aqueous solution. That's going to make our lives easier, because if everything were solid, they just wouldn't react because they just sit there. It's like if I put this pen, this solid pen, on this solid book, you can imagine what a difficult time they would have reacting. Yes? Because they just don't interact that much. So let's take a look at our first one. Here is zinc. I want you to look up at the top of zinc. Top right-hand corner of zinc. What is there? What is in the yellow? Nothing. Why is there nothing there? Because it is in its elemental state. It is by itself. It is neutral. Okay? So this is elemental zinc. And therefore, it has a 0 charge. It is by itself. It has a 0 charge. What state is zinc? It's a metal, and all metals are solid. Not mercury, but close enough, okay? So it's a solid. Do you need to be able to predict these states? Not 100%. Okay, if you want to look up at the top, you can say, oh, look, it tells me that metals are solid, fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. I'm not expecting you to know those things, okay, but they're there just to help you write these in this particular context, okay? Now, all of these are taking place in aqueous solution, but even if we throw some zinc into some water, it's still solid, yes? So if you throw some metal in water, it just stays metal, okay? Silver nitrate. It's got nitrate in it. What does that tell you? It's soluble and therefore it must be aqueous. What is the charge of silver in silver nitrate? Tell your partner, what is the charge of silver in silver nitrate? Feel free to use your pink sheet if you want to. And if anyone has forgotten their pink sheet, you can come and borrow one of my white ones here. Yes. Oh, my grade 11s didn't know what happened when you put salt in water and stirred it. Right? And they're like, I don't know what it looks like. And I'm like, okay, so we're going to dissolve some salt in some water. To be fair, about half of them knew what it looked like. Half of them were like, yes, I know what that looks like. The other half were like, I don't know what happens if you put salt in water and stir it. It just looks like water when you're done, right? Because it is completely dissolved. Anyway, they didn't know, so we did it. And it's just like normal salt because it's cheap. All right, silver nitrate. Charge of silver is +1. Nitrate is -1. Okay, we know it's an ionic compound because we have a metal and a polyatomic ion. Now, who is zinc going to replace in this double replacement? In this single replacement, thank you. It's going to replace silver. So we're going to take our zinc and it's going to replace the silver. So the first thing I'm going to do, and I'm going to do this this way because I would like to, silver is now being kicked out. Silver is now by itself. Silver is by itself. Is it combined with nitrate anymore? No, it is no longer with nitrate. If it is by itself, what is its charge? It is 0. So we're going to have Ag with a 0 charge. I'm going to write it up here, but normally you would just not write anything, okay? And Ag is a metal, therefore what is its state? Its state is solid, okay? Now the zinc has kicked out the silver, and now zinc is combined with nitrate. Is it possible for zinc with a 0 charge to be combined with nitrate, which is negative? No. If you've got a negative ion, you also need to have a positive ion, which means that zinc is no longer going to be neutral. It is going to be, it's going to be a charged ion. And what charge does zinc become? Feel free to look it up if you want to. Zinc is +2. So we're looking at now zinc 2+, and NO3 is negative. So what is the formula for that compound? ZnNO3 2. Okay, and because it's a nitrate, it is soluble, so that is going to be aqueous. Before we do anything else with this, what should we do? Yes, we should balance it, okay? Would you guys know how to balance this? Do you want to try balancing it on your own? And then you can check with me. Okay, so we have 2 nitrates. We also need to have 2 nitrates. So we're going to put a coefficient 2 here, which means we also have 2 silvers, which means we need to put a 2 here. And I think that does it, doesn't it? Yeah? Okay, so that's good. Now we are going to write our complete ionic equation, doing just what we did before. If we have aqueous ionic compounds, they are going to, what's the word? Dissociate. So zinc solid, is that an ionic compound? No. So does it dissociate? No. And besides which, it's a solid. Okay, so we're just going to leave it alone. So we still just have zinc solid. Now we have AgNO3 and it is aqueous. So is it ionic and aqueous? Yes. If it is ionic and aqueous, we separate it. So let us separate it. Don't write down what I'm writing down. I want you to critique what I've written down. Okay, so it's not 3 NOs, right? It's NO3. Okay, that's good. What else is wrong? I need to have 2 NO3s because I've got that coefficient 2 there. I also need to have 2 AGs. Anything else missing? States. The silver is aqueous and the nitrate is aqueous. Now here's a question for you. This silver here, is it actually on its own? Or is it part of a compound? It's actually part of a compound, right? We can see that it's part of the silver nitrate. So it's part of a compound. So is it elemental? No. So it has a charge. And what is its charge? Positive. Okay? And then, of course, nitrate needs a negative charge. Do I do anything with the silver on the right-hand side? Or do I just leave it alone? Leave it alone. 2 Ag. And why does it have no charge? Because it is an element on its own, not part of a compound. Zinc nitrate aqueous. Do I need to keep it together or do I need to split it? Split it. Why do I split it? Because it is both ionic and aqueous. So I'm going to split it apart. Zn 2 plus aqueous. How do I deal with the NO3? How do I write that? 2 NO3s. Okay, so plus 2 NO3 aqueous. Charge negative. Now I want you to notice how this is different from a double replacement reaction. In a double replacement reaction, I started with Cu2 plus on one side and I finished with Cu2 plus on the other side. It did not change charge. What is happening to the charge of the zinc? It's going from nothing to 2 plus. How about the silver? Silver's going from positive to 0. So in single replacement reactions, elements go from being charged to being uncharged, or they go from being uncharged to being charged. So it's a little bit different. What's really happening is we are transferring electrons from one substance to the other. So in this particular case, we would transfer some electrons from the zinc to the silver. The silver would gain electrons and become neutral. The zinc would lose electrons and become positive. Okay, don't worry about that too much. I'm just bringing it up because our last unit, Unit 6, is called electrochemistry, and it's all about the transfer of electrons. So this is what we call a reduction oxidation reaction. So we have one thing losing electrons and one thing gaining electrons. So all single replacement reactions are about the transfer of electrons. How about double replacement reactions? Are they about the transfer of electrons? Or did everybody keep the same charge from side to side? Everyone kept the same charge. You had a question, sorry.
Okay, sorry, I think you said by nutrient it's similar times I, although the products is both glucose modules, I don't know what's very the ion is like, why does it dissociate?
Why does it dissociate?
Well, wait, does it dissociate?
The zinc nitrate?
Yeah.
Yes, it does.
Okay.
And why does it? Was that your question?
Yeah.
Okay. You just have to look at the compound, and then you would go back to your data pages and you would say, this is all taking place in a beaker with water, okay? And if it's all taking place in a beaker with water, and I have nitrate, and it's pairing up with zinc or anything else, it's going to be soluble. So all single replacement reactions are basically going to be, I have a beaker, it's got maybe some silver ions in it, and it's got some zinc solid, right? And it's got some nitrate ions in it. And we're going to look at what happens there, but it's all taking place in water. So that's why it's going to be aqueous. Yeah, good question. All right. So now let's take a look at this. When we do our net ionic equation, we need to look for spectator ions. Spectator ions should look identical on both sides. Who looks identical on both sides? The 2NO3. Okay, 2NO3, aqueous. 2NO3, aqueous. So when we're asked what our spectator ion is, we're just going to write NO3. We're not going to write 2NO3 because that would imply that out of the millions and billions and trillions and quadrillions of nitrates, only 2 of them are spectator ions. But in actual fact, all of them are spectator ions. So we're just going to write NO3. Does that make sense? The 2 is just to do with the stoichiometry of the reaction. Yes. Pardon me? No. No, if you're asked what the spectator ion is, it doesn't matter what state. Spectator ions will always be aqueous. So it's almost like not worth it. If you wanted to, though, it wouldn't be wrong. Okay? Yeah. So how would we then write the net ionic equation? All we would do is we would not write the spectator ions. So we would write Zn solid plus 2Ag plus. I really did not leave myself enough room here, did I? 2Ag plus aqueous goes to 2Ag with no charge solid plus Zn 2 plus aqueous. The nitrates are still there, they're just not doing anything. Yeah? The reason that we're focusing on this is because what if I asked you, could we monitor the rate of this reaction by observing the nitrate concentration? Could we measure the rate of this reaction by looking at the change in the concentration of nitrate. Tell your partner what you think about that one. And if your partner's asleep, wake them up and ask them. Could we measure the rate of this reaction by looking at the change in the concentration of nitrate? Has the nitrate actually changed at all? Have we used it up? Have we produced it? Has it just sat around and done nothing? Yeah, so you cannot. So spectator ions can never be used to measure the rate of reaction, which is why we're bothering with all this ionic reaction stuff right now, okay? Because that's how it fits into our reaction rates unit, okay? Oh, pen stopped. We're going to stretch and then we're going to do one more question and you guys are going to work on some stuff, okay? So, let's stand up, 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 up. Okay, does anyone have I know what we're going to do today. I don't know if you can do this, but you can hang on to your desk if it's too hard. Okay, so what we're going to do is we're going to take our foot and we're going to cross it like that, okay? And then we're going to kind of sit. And you're going to stick your bum out. And you can hold onto your table if it helps you. And you should feel a stretch in your butt cheek. And if you're not feeling a stretch in your butt cheek, you're doing it wrong. And you can do it without hanging on, but you can also hang on to your table because it just makes it more comfortable. Oh. This is a really good one to do if you sit a lot, because when you sit a lot, it's really bad for your hips. We're going to do the other side. Okay, so cross over, and we're going to sit down. Oh, that feels really good. Okay, another one we're going to do, because we spend a lot of time bent like this. We're going to kind of do like a little lunge. Okay, so we're going to lunge down, but then you're going to press your back butt cheek forward. So you're actually trying to stretch the front part of your hip. So you might need to turn sideways. Okay, your feet are pointing forwards. I'll get up here so you can see. Okay. So what you're doing is your feet will be on the same level, right? But what you're going to do is you're going to bend your leg, and then you're going to tilt your hips like this. And you should get a stretch here. And you can kind of lean back a little bit if you're flexible. And if you're not flexible, you can just do that. Oh, that feels good. Okay. And then you can change sides. Okay. Okay, we're going to do one more example. I would let you do it on your own, but I found we don't have that much time left. And I found with my other block, they needed some support in this. If you want to try it on your own, feel free, just work while I'm yakking up here. What kind of a thing do we have here? We have a diatomic element. Now, do you guys need a review of who the diatomic elements are? Would anyone like it for their periodic table? I'm going to pull it up just in case. Do you see the blue ones? If you start on element number 7, which is nitrogen, and then you draw a 7 down to iodine, that gives you 6 of them. And that's your hockey stick. Okay? And then if we go over here, that's the puck. It's very Canadian, yes? So we have our hockey stick. Starting on element number 7, draw a 7. And then you've got your puck is the 7th element. Diatomic elements are only diatomic when they are in their elemental state, when they are on their own. Okay? And that's going to be important in this next one. So this is diatomic. And it is also elemental. So what is its charge? Its charge is 0. It's neutral. Okay? Now over here, what do we have? What kind of a thing is that? K and I together. That's an ionic compound. And remember, everything is taking place in aqueous solution. So we've got that beaker full of water. Okay? So Ki is going to be aqueous. Who is chlorine going to displace? Iodine, because we have a nonmetal, it's going to displace the nonmetal. So it's going to come over and it's going to kick out I, and I is going to be on its own. And when I is on its own, it is diatomic, it's elemental, yes? It's diatomic and it is what charge? Diatomic. And it is also neutral. So we're going to write I2 over here, I2. And it just so happens that at the top of the page, I've told you that I2 is solid, but I don't really care if you know that or not, okay? So you can look it up there, it's a solid. All right. Ki, we just kicked out the I. So who's going to take I's place? Chlorine. Now, is it going to be chlorine 0 when it's in that compound with K? No. What charge will chlorine take on when it's in the compound? It's going to be -1 because chlorine is in group 17. All group 17 are -1. So we have K plus is going to combine with Cl minus. So what is the correct formula? KCl. And it's not diatomic because it's not elemental. Okay, KCl. And what state will that be? That will be aqueous. Now we need to do some balancing. Could you guys balance that? Give it a go. Yes. Chlorine is a gas. Yes, chlorine is a gas. Okay, hopefully you put a 2 in front of the KCl and a 2 in front of the Ki. Yep. Complete ionic equation. Are we going to take the Cl2 and split it apart? Is chlorine aqueous? No. Even if it was aqueous, is it ionic? No. And if it's not aqueous ionic, do you split it apart? No. So it fails on both those accounts. It is a molecular compound. It's not a compound, but it's a molecule. And do you remember what happens with molecules if you put them in water? They stay intact. Do you remember that from Tyler's little thing here? Right? When we had molecules, they stay intact. So if we had Cl2 and we put it into the water, it would just stay as Cl2 and it wouldn't break apart because it's a molecule. Okay. There we go. All right, so it's not going to split apart. So we're just going to have Cl2, which is still a gas. We do have an aqueous ionic compound. You can tell me what you think of that. No. What am I missing? Charges, K plus, I minus. States, aqueous, aqueous. What else am I missing? The coefficients, I need a 2 and a 2. And you'll notice, iodine, is iodine on its own here? No, because it is part of Ki. And because it is not on its own, it's not diatomic. Okay, it's only diatomic when it is on its own. Here it's part of a compound still. However, once it makes it over to the other side, it has reacted. It has gotten rid of its extra electron. Okay, 2 of them, they've gotten rid of 1 electron each. And now it is on its own. So it stays as I2. And then finally, I bet you guys could do this without me, yes? Can you finish it up without me? Yeah? When you're finished, you can check up here and see if you did it the same as me. Who are your spectator ions? Potassium. And anything else? Nope, just potassium. Do I write 2K plus or do I write K plus? Just K plus, okay? We don't write coefficients when we're just naming something. It's like if I said, who is the solvent? You wouldn't write, 2 water if it said 2 water in the equation. You would just say water is the solvent, okay? So you would just write your reaction, your net ionic reaction as Cl2 plus 2I minus goes to I2 plus 2Cl minus, and then of course you would have to go through and put in all your states. Okay. And your job between now and tomorrow, and you have 15 minutes to work on it right now, is to finish 0.2b and 0.2c. I'll figure out what pages that is in just a second. Okay? Pages 21 to 24. Okay, pages 21 to 24. Hi. Of course. So I'm going to come around and try and learn the names of people who I don't know yet. Okay, and I'll come around, and if you have questions, wave me over. All right, if I don't get to you right away. All right, let's see who I know. Of course. Yeah. Oh, yeah. Just it's I've got it to this. Yeah, but the problem is I sold it my very low and I made a few solid on it. So you don't have to. It's my fault for not customizing this for the grade 12. Yeah. Yes, of course. Yes. Okay. Close. Pages 21 to 24. That's 0.2b and 0.2c, but you can just do, it's easier sometimes to just know the page numbers 21 to 24. Okay. Hi, and you are Shauna. Okay. I'm sorry. Yeah. Oh. Yeah. I saw you, I saw you. And I was like, I'm here first, wait a minute. And you're in two grades. I hear you. Oh, this is okay, but just in general. Oh, that's a lot. Yeah. I don't always. I feel it's more fair for people. Yeah, we do have, all the research. Oh, that's all my. They're all. They all have to. Yeah. But it's just like, was it semester one? Semester two. Oh. You look a little. Okay, that's why. Yeah. I know. Stop.